Yeah. So welcome everyone. It's our pleasure to have Xinbiao here to share about his work in our seminar. And today he'll be kind of share some new insights about what is the pros and cons of having quantum entanglement in quantum machine learning. This will be some kind of like surprising insight because we never expect that to happen. So I think like Xinbiao will be able to tell us a bit more, and Xinbiao, like the floor is yours.
Okay. Thanks for the introduction, and I'm very glad and honored to give a talk here about our recent work, transition error or entangled data in quantum machine learning. And this work is done when I'm intern at JD Explore Academy under supervision of Yuxuan. And this work is also collaboration with Zhuozhuo Tu, Yongluo, Xiaoyan, and Da Chuntao. So if you are interested in this work, maybe you can refer to this archive link. So let's begin. So to have common background on quantum machine learning, so I'll first give a brief review about quantum machine learning. Generally speaking, quantum machine learning is that's machine learning algorithm related to some quantum stuff, like using quantum algorithm or quantum data. And that some difference with machine learning and conventional quantum algorithm. In machine learning, that could not be involved quantum data, and in conventional quantum algorithms, the difference is that machine learning aim to learn or construct the model according to data and generalize this model to infer on unseen data. But traditional quantum algorithm just construct a model for a specific task, and if we have another task, we have to train another model or construct another model. So basically, most of current quantum machine learning algorithms are quantum classical hybrids, and the paradigm is the following: that's giving input state psi j, which could be obtained by encoding classic data in quantum states or prepared from quantum experiments. And this input states taking as inputs into a quantum system, and we then use measurement to read all the classical information, and finally classical computer processes classical data, and basically classical computer maybe acts as an optimizer or just post-processing the classical data. When it acts as an optimizer, and this paradigm may be related to quantum networks, and the quantum network can be used to accomplish some classification task, like for mean-state data or quantum phase, and it also can be used to learning unitary. And when the classic computer acts post-processing, maybe this could be related paradigm to relate to the shadow algorithm, like the awesome class shadow, and it can be used to estimate some properties of quantum system, like the local observables, quantum fidelity, two-point correlation, and entanglement entropy. So a general formula, so to summarize, a general formula for machine learning algorithm consists of the three elements. First is the type of states. The states may be entangled, unentangled, or match states, or coniferous states, or stabilizer states, or something like this. And the type of second is the type of quantum circuits used by the learner. And the quantum circuits could be consist of some deep layer quantum circuits, and maybe they consist of coniferous gates and the tickets. Okay, so the final element is the type of measurement done by the learner. The measurements could be entangled or unentangled. So modify any one of these parameters can change the quantum learning model. So when it came to this, how about we can talk how to say the learning model is bad or good. So we'll give 3 evaluation metrics for learning algorithm to give the answer of the question. The first is the generalization error, which measures the ability to accurately make prediction on unstable data. And this is very important in the machine learning theory. So the second is sample complexity, which we define as the training data size used by the learning algorithm. And we know that the definition of sample complexity may be different in quantum machine learning and classical machine learning. And in machine learning, its definition is just like this. But in quantum machine learning, when we talk about sample complexity, maybe more refer to the number of copies of the states used by the learning algorithm. But for simply, we denote this as a query complexity. That is the number of copies of the input states used by the learning algorithm, and the sample complexity is still at the training data size used by the learning algorithm. So most quantum learning algorithm with quantum advantages in terms of just the evaluation metric we gave just now, and this algorithm maybe most of them share the common feature that is entanglement, or more specifically entanglement or across many body systems. And a typical instance is that a serious work done by Xinbiao that they use the entangled measurements to estimate the properties of some observables. And they show that if we use entangle the measurements to do such tasks, it can reduce exponential sample. It can lead to exponential sample of exponential query complexity. To compare with then that without using entangled measurements. So the second instance is that it's obtained by the work of Xunbiao Zhuang. Yes, they use the entanglement in quantum dynamics, and particularly they use this entangled dynamic to prepare entangled problems for some sensor tasks, and the probability error of detecting a target will be exponential reduced compared that with just using unentangled problems. So how about the case when incorporating entanglement into the data? And the work of Shamakula, they show that using the entangled data can exponentially reduce the sample complexity for achieving zero prediction error. So let's see how they get this result. So they consider a unit learning task. Specifically, they like to learn the target unit array from the hypothesis sets. And this unit array is in n-cubic hyperspace, and its dimension d equal to the n. So to complete such task, they use the entangled states. Almost specifically, this entangler is mean that it's in the sense that two body entangled states. Yeah. So the entangled state has the following form. And this is the Smith decomposition expression. Yes. So and then they consider the training data sets as input states are psi j, and the output is phi j, and phi j has this expression that is the tensor product of U and the identity matrix in the Hilbert space H sub R. And this using this unitary acting on this input states. So they assuming that if the learning process can achieve the perfect training, that means the training error is zero, and mathematically it can be expressed as the inner products between the output states of unitary and the output states of hypothesis is 1. So this means that the output state or the target unitary and the hypothesis is the same up to a global phase. Yeah, so we consider the response function as the evaluation metric, and the response function is the higher average of the trace norm of the difference between the output state target unitary and the output state of hypothesis unitary. Yeah, so they show that the normal bounds of this average the response function and the average it over U and the training states, training data sets SQ. So the normal bound is 1 minus d plus square of R times n over d times d plus 1. So so how we can get from this normal bound, and maybe we can say from two extreme case, that is R equal 1 and R equal d is the dimension of the Hilbert space. So R equal 1, this means there's no entanglements in this input state. So when we want to achieve a zero prediction error bound, we must need to enlist n equal d training data size of n. Yes, the training data size of n equal d. So when we use highly entangled states, that means R is equal D. And in this case, one example, that means N equal 1. It can achieve the zero prediction error, because when R equal D and N equal 1, the numerator in this formula it equals the denominator, so it can achieve zero prediction error. So that's why we say that using the entangled data can exponentially reduce the sample complexity for achieving zero prediction error. Additionally, they also show that in the classical case, this normal bound is just at the case of R equal 1. That is an entanglement case.
Sorry, I have a question over here. Do you assume have any assumptions on the dimension of the reference state, H of R? Any assumption?
Okay, the reference system is equal the dimension of reference system is equal the system X. Okay, so because in this case the large the entanglement degree or smear rank is less than D. Yeah,
so what happens if you have higher dimension than the system size? Like
because this if we enlarge the reference system, it doesn't it's the same as the dimension of the reference system being D, because we just consider the input states in this system X, because the target unitary we would like to learn it's in the system X. So if we enlarge, for example, if the semi rank here are equal namely 2 times d, so it will need the 2 times d orthogonal states. Oh, sorry. To form this to form this entangled state. Yeah, just what I mean like that. If the dimension of reference system is larger than d, but there is at most the orthogonal training states in the system X. So it doesn't make sense if we enlarge the reference system, because we only consider the system X. Yeah, or you can learning from another aspect. You can consider entangled states as a mixed states by partial tracing the system the reference system. So in this regard, the entangled states become the mixed states. Like here is the cat CJK and Braque CJK. So and the CJK is orthogonal for different J and K. So this states maybe at most have at most rank D.
Mm-hmm.
Okay.
Yeah, I see. Yeah. It's I think it's clear why we don't really want to go like larger dimension for the reference states. Yeah.
Okay.
Yeah.
Okay,
Thanks.
Okay, so go ahead. So it's the end of the story, but actually we know some caveats in their work. That is, first, they consider the measurement is infinite, the number of measurements is infinite, and they don't consider the statistical error of the statistical measurement error. And the second is maybe they consider the coherent learning protocol, because that's in practical setting, this is maybe hard because maybe we don't have access to the target system U, and maybe the target system U and the hypothesis or the parameterized quantum circuits are complement on different hardwares. So this is not practical. The third is preference training assumption. And so in analytical setting, this could be achieved because there almost exists the statistical error, even though in the fault tolerant algorithm. So we cannot achieve preference training assumption. So how about power or entangled data in a more realistic setting? So let's we go in our realistic problem setting. So we use the same entangled states and taking it as inputs into the target unitary and the hypothesis. But instead of learning the whole unitary, we aim to learn the function like this, trace of U psi, Braque psi U dagger O. So in this case, we can just do measurements on separately on these two unitary, and we don't need to the preference training assumption. Here we adopt projection measurements as the observable, because any observable rate of the class information from the quantum system by the eigenvalue. So we consider the projection measurement here. And in this case, the training data set consists of the input state Psi and the outputs OJ, and where OJ is the empirical estimation of the expectation value of O. So here we also consider this function like this, the hard average of the trace, the square error of the trace expectation of O with respect to targeting tree and hypothesis. So in this setting of finite number of amendments, so the question is that does entangled data still contribute to quantum advantage in terms of sample complexity? And here we show that if we assume the training error is less than F0 and the average function, it will be null bounded by this formula. So so this formula is related to the number of measurements M to the training data size M and the entanglement degree R. This could be the smear rank. So we can get the following implication from this null bound, and we will give a discussing about the prediction, about the impacts of these parameters that M, M, R on the prediction error. So first, we look at the smear rank R, and we can say from this formula that entangled data has a dual effect in prediction error. What I mean by that, the entanglement degree of smear rank R plays a different role or plays a opposite role in the effects to this average risk function. So for the positive effects, if the number of measurements M is greater than R square or R times N, then this minimal term is dominated by this term. Yeah, so in this case, if we increase the smear rank R, and we can increase this term and decrease this term, so entangled data, highly entangled data will lead to a small prediction error. And we also consider two extreme cases that of R equal 2 to the N and R equal 1. So we can say that R, in the case of R equal 2 to the N, still can still achieve an exponential reduction in terms of training data size compared with the case of R equal 1 for achieving a sufficiently small prediction error. So this equal with the results achieved in that of Kurashima. So for the negative effects, if the number of measurements is less than square root R times N, then the minimal term is dominated by this one. So in this one, the smear rank is in the denominator. So if we increase it, then we can decrease this term and increase the prediction error. So in this case, the highly entangled data do not only require a large amount of quantum resource for preparing, but also need to a large prediction error. So let's turn the attention to training data size N, and N is in here. So it's clear to say that increase in can constantly decrease this prediction error. And for the number of measurements M. So we can say M is here. So we can say that while M contributes to a small prediction L, but it's not decisive to the ultimate performance of the prediction L, because when the M grows infinitely, this minimum term is dominated by this term, so it's independent with the number of measurements. So the ultimate performance of this prediction L is determined by the training set N and the semi rank R. So this tells us if we want to actualize the power of entangled data, we need at least M greater than R. So sorry, that's not R times N measurements. So this should be square of R. So this also suggests that the number of measurements should be stats adapting to the entanglement degree of the input states. So having discussing on the on the training side and the number of measurements and the semi rank R, we will talk about how the prediction error depend on the query complexity. So we can say from this, the lower bound of query complexity for achieving the efficient small prediction error is like this term. So the important point is that we found when the semi rank R equal 1, this matches the optimal lower bound for quantum tomography with single covalent adaptive measurements. And this have been improved in the work of low angle stats lower bounds for learning quantum states with single covalent measurement. And I think this work is more interesting and writing well. So particularly in this task, we aim to learning the target operator U dagger OU, and this is actually can be depicted as this paradigm, as that way input input passage, and we want to learn U dagger OU through measurement this input state, and this could be regarded as the dual problem of quantum tomography pure states. And in this case, we can exchange the location of U dagger OU and passage. In this case, we can regard the U dagger OU as the input states and passage. And this is passage is a partial trace of passage, and as the semi rank equal 1, so have just one term. So this could be regarded as a dual problem, and sorry. And the angles they show that the lower bound for quantum for tomograph sexual states is like this. That is the square of D over L times square tilde epsilon. And here L is the number of outcomes, and specifically L is the possible outcome of measurements used. So here if we use the projective measurement situation, then the possible outcomes so we can say we can compare these two terms, and when L is a constant, and we can drop it, and R is equal 1, so these two terms are exactly the same. Yes, so we say that this matches the optimal lower bounds maybe verify the tightness of our derived neural bond. So maybe we will get more intuitive understanding from the proof idea. So I will take some time to give some proof sketch. So recall that our aim to learning a function that like trace or you row from the hypothesis that yes, well, just when it belongs to special unitary or dimension D. So this task is hard when this hypothesis set contains a large amount of very different operators, and particularly it may contain infinite many operators. So a solution to this problem is discretizing the hypothesis set by constructing the epsilon packing and had the definition of epsilon packing. So for surely, epsilon packing is just so this is the epsilon packing. It's just a discrete subset of the hypothesis set F, and in this if the packing for any elements any element f sub 1, f sub 2 in this packing, the distance between f sub 1 and f sub 2 certifies that the distance between them is greater than 2 epsilon. So the finger is like this. So this point, this center point of the ball or the epsilon ball, yeah, this is the epsilon ball. It's epsilon packing, and this points consists forms a discrete set. Okay, so we can say that any two H ball are disjoint. So this point this needs to that the points in this even packing are well distinguished, which is a very important properties for our derivation of the neural bonds. So even though we describe this infinite sets as with finite epsilon pack, so it's maybe still hard to directly derive the neural bond from according to main problem. So here we attempt to reduce the learning problem to a hypothesis testing problem, because there are many tools developed for hypothesis testing. So we do this. So first, if we naturally choose X from graphical sub 2 epsilon uniformly, yes, we just uniformly uniformly sample the points from the epsilon packing, and we denote u sub x as the unitary operator, and then we're giving some input states, and we evolve this states through the target unitary ux and measuring the evolved states and O, and we can obtain the training data. And third, we maybe could employ some learning model to optimize a predefined loss function, and we can obtain a null hypothesis H sub S. This means that the null hypothesis is dependent on the training data. So first, we conduct hypothesis testing like this to find the estimate in text that's it. Close this to this null hypothesis, and we denote the probability, the error probability of this hypothesis problem as this. Yeah. So why can we do this? So this number give a theoretical guarantee to this reduction. from learning problem to hypothesis testing. And we can say from this lemma, the average prediction error is not bounded by the average error probability of the hypothesis testing problem. So now we just need to not bound this average the error probability of hypothesis testing problem. So because as we just mentioned, there may be some tools to do this to bound the probability error of the hypothesis testing problem, and follow equality is the one, and this equality gives information search bounds on the probability error or hypothesis testing. So we just only look at this bound. So through this follow inequality, we can reduce the lower bound of error probability like this to after bounding the mission phasing between the target index X and the estimate unitary index S hat, and lower bounding the cardinality of two-issue packing. Yes. So these two quantity, we can have many tools to bound these two quantity, just from the information theory or statistical learning theory. Okay, so let's maybe next we aim to bounding the cardinality of shared packing. Maybe this could be some take more much time, so we just skip to the final lower bound. Basically, we can get packing, two-issue packing, and with whose packing cardinality is larger than exponential about this system. So we next to bounding the mutual information between the estimate X and the target unitary X. So this could be more important because the conclusion or transition error comes from this bound, because we can say this minimum term and the entanglement degree, one is in the denominator and one is in numerator. This is the leads to the transition error of entangled data. So let's give an understanding about this minimal term through the Markov chain. That is that we sampled random index X, and you employ the related target unitary to evolve the input states and get output states, and we then use the observer O to read out the classification, and we get OJ. And finally, we use OJ to estimate the target index, and the estimated index is denoted as head X. Sorry. So here we use the data processing inequality to separately obtain this two terms in this minimum. So the first we use the data processing inequality that the observation from the Markov chain. That means the information between X and head X is less than the information X and the intermediate random variables O sub j. And we can obtain the upper bound of the distribution information. And we ignore the detailed proof techniques, but give into understanding about this upper bound. So it's clear to think that if we increase the number of measurements, we are learning about the output states, and so we can get more information about the quantum states. So this increasing the number of measurements and enabling more information extraction about the quantum states. So a large M will need to large mutual information. And for the small rank R, a large R will increase the information density. Maybe this is defined by myself. So this increases information density of the output states, and hence decreases the extracted information amount by single projecting measurement O. Maybe we will have more deeper understanding later from the numerical simulation. So we just skip this. And on the other hand, the mutual information between the estimated index S hat and the target unitary X is upper bound by the mutual information between X and the output states according to the data processing inequality. And this information is less than R times log D, because the information or the target unitary contained in a single output state is limited. So if we increase the number of measurement M to infinite, we only can obtain the information from the single output states. So this is just a row of this unitary, this target unitary UX. So we can get an upper bound, infinite upper bound by growing M to infinite. So a highly entangled output, but we can say that if we increase the entanglement degree in the entangled data, and it's maybe obvious that a highly entangled output state contains more information about you than a lowly entangled output state. So we can say from the numerical simulation more clearly, and we'll present later. So let's look through the whole proof process, and from the outside direction. So first, if we can obtain the bound about the two-issue packing cardinality and the mutual information, then we can using this two bound to lower bound this probability or hypothesis testing problem, and then we can use this to bound the average risk function. So finally, we get the lower bound of the average prediction error. So like this. So this is the full term about the average prediction error. So we conduct numerous simulations to verify the theoretical results. Firstly, we construct the target unit stats. Particularly, the target unit stats we construct is like this. That is, we pick the unitary whose put some entry in the first row is A to I gamma sub j. This means that this row, the j and j's entry in this row being like this, and the other entry being 1, because this is due to the definition of unitary. So if we choose the observer O as a computational zero basis, so a substantial set of target operators we like to learn is like this. U take OU is just the computational basis, and J is belong to the discrete sets 1, 2, 3, and to D. So in this sense, if we let U star be the choosing target unitary, and the learning U star take OU is equivalent to identifying the unknown index K star, because in this learning task, you start take OU just choosing from this the computer basis. So let's go ahead to say the construction of entangled data. We record that the entangled data has the Smith decomposition form, and well, the sum of CJK equal 1. So we know that the observer O is on the subsystem X. So we just consider the mixed states sigma J. Yes, it has this form. So here the mixed state set is just like this, and we consider the CJK is just random choosing from combination basis 2, and here the pi refer to the permutation operator, because the combination basis in this mixed states is not need to be ordered well or successive. Yes, this index is may not need to successive. So we just using this mixed state as inputs, and we get the out state, and then we use the observer O to obtain the measurement outputs like this. So this are training data set. So finally, we would like to estimate the unknown index. This could be done by collecting the measurement outputs over all possible index k. This means that different k means this measurement outcomes is generated by different unitary. So we can determine the target estimate k hats by minimizing this function. So let's say the condition for correctly identifying K star. Yeah, because the first is the state that, yeah, this is the mixed state, the computer basis in the mixed states. If we would like to correct identify K star, this set must contain the target unitary or target operator U dagger OU star. This is this matrix form of the pure states. So this is because if this set doesn't contain this operator, then we can yes. So look this. So if we think R equal 1 and equal 1, if this set not contain the U dagger or U dagger, in this case is the to say 1 1 it did not equal A sub k star. So the output O sub 1 is always 0, so we can't correctly identify k star. And the second condition is the measurement output should closely approximate the corresponding Smith coefficient say k star of the operator. Because if we using this target operator to measure the mixed states, and the coefficient is so small, we maybe need to closely approximate the coefficients, and then we can correctly identify. So we give some explanation from these two extreme cases, R equal 1 and R equal D. So first, if we let R equal 1 and the training data is just 1, and so there is only one Smith coefficient C11. O sub 1 is always 0, so we can't. So no matter how much, how many number of measurements we use, we always cannot identify this target index k star. But if the pure state is exactly equal or the same as the target unitary target operator like this, we just use few number of measurements and we can identify the target index k star, because in this case C11 is equal 1. So if we use the target operator to measure this pure states, we can always get 1. So it's easy to identify these two operator. The two density matrix is the same, and so we can identify the target index k star. But in the case of the Smith rank being 16, this is the dimension of hyperspace, and the primitive size being 1. So in this case, the target operator always belongs to the state sets like this. So in this case, the output state O sub 1 is always non-zero if we use a large number of measurements, and so we can always. So if we using a large number of measurements, we can always identify the target index k star. But this maybe need a more number of measurements than the case than this case that R equal 1, but the pure state is exactly the operator, because in this case the coefficient, the Smith coefficient is equal 1 of D in the average sense. So if we would like to identify the k star from according to this their coefficients, we must employ more number of measurements to closely approximate this Smith coefficient. So that's why. So that's why entangled data contains more information than unentangled data, because we can say from this two extreme case. So and another is that why entangled data, why the information why projective measurements is hard to extract information from entangled data, but it's easy to extract information from unentangled data. So that's because the larger the Smith rank is, the average the coefficient, the smaller this coefficient is. So the large number we need to identify this target in that case study. So here the numerical results, and we aim to learn a 4-qubit unitary U, and here the z-axis is the precision L, and this axis is the semi-rank R, and the y-axis is the number of measurements M. So, and we plot the case of training data size being 2 and the case of training data size being 8. So we can say from this figures that when the number of measurements M is small, so it's ranged from this direction. Here is small and here is larger. Okay, so when the number of measurements is small, if we increase the semi-rank R, the precision L will first decrease and then increase when the semi-rank R pass some threshold. So this verify our theoretical results. And when we increase the number of measurements, when the semi-rank R is small, the precision L is just keep the same. But if for when the semi-rank is large, increasing the number of measurements can decrease the precision L, and in this case, like this, n equal to, we just need the training data size being 10, then we can achieve the 0 precision L with the maximum with a larger number of measurements M. So additionally, we can see from this figure, yes, the y-axis is precision L, and the x-axis is the training data size, and the line with different colors and markers refers to the setting with different semi-rank and the number of measurements. So we can see from this figure, when we increase the number of the training data size, the prediction L constantly decrease, and when we vary the semi-rank R and number of measurement M, we can get the same results like we see in these two fingers. So here is a numerical simulation result with oscilloscope training states, and in this case, this oscilloscope means that the different training input states are oscilloscope. So so due to the definition of the semi-rank decomposition, the number of the training data size N and the semi-rank R should satisfy their product is less than the dimension of hyperspace. So here for the training data size N being 4, the maximal semi-rank R is 4, and for the training data size N equal 8, the large number, the maximal semi-rank R is less than 2. So maybe we can clearly see from this figure that the trend like we just seen in last slide, that if for small number of measurements increase the semi-rank R, first first decrease the precision L and then increase the precision L when it's past the threshold L is 3. And here is the final simulation result, and this this is heat map, and the dark turn is the color is the printing area is larger. So the y-axis is mirroring R, and the axis is arranged from left to right by the magnitude of product M and N. So this means that this is the number of measurements, and this is the training size, and in the this tuple in the right side is larger than that in the left side. Yes, this is their arranged according to the magnitude of the product. So we can say that for small number, for small smear rank, and when the query complexity, because the product on M and N means the query complexity, and for limited complexity, with the wrong assignment about the number of measurement M and the training N, maybe the query complexity, a large query complexity maybe have a large prediction error than small prediction than small query complexity, because yes, you can for example like this two, yeah, here the number of measurements is 5,000 and the training data size is 2. Here the number of here the number of measurements is 500, but the training data size is 12. So the query complexity in this case is larger than this case, but the printing error of this case is less than is larger than this case, just because we assign too much query complexity to the same training data size. This means we gave each training data size 2,500 copies, but this we give fewer copies of each training data size. So this means we should carefully arrange the query complexity to the number of measurements and the training data size. So this is all. So maybe if you have any question.
Yeah. Thanks, Xinbiao, for the very interesting talks, and yeah, I like the way that you kind of present your results and shows all the proof reductions and simplifies kind of pinpoint the kind of quantities, for example, mutual information and the size of the epsilon nets that you have to kind of bound, and then you use that to kind of basically lower bound the kind of expected risk for your framework. For the audience, if you have any questions, you can unmute yourselves or type in the chat, and I could help you ask it. And maybe I could start off by me asking the questions do you have any technical considerations of why to just restrict yourself on projective measurements?
So
actually,
actually,
projective measurement is quite restrictive, right?
Yeah, actually, because the transition error maybe exists for weak measurements. That means weak measurement just means the outcome of this measurement is constant. And in this case, it's hard to extract information from the entangled data by this weak measurement. So this weak measurement is not just as we think in quantum algorithm, but we define it as the constant outcomes. Yes. So in this case, the entangled data contains more information, but the weak measurements have not the ability to extract the information from it, and even it can the extract information may decrease with the increasing the smear rank. So this is why the transition error occurs. But if we consider measurements with many outcomes like exponential outcome like any POM measurement. So this transition rule maybe not occurs because no matter how the information the entangled data have, a strong measurement can always extract all information from this input state. So that's it. So if we consider the projective measurements, we can get this result. But on the other hand, maybe the project measurements is easy. It is easy to implement on the practical quantum experiments.
Yeah, typically we would just like do computational basis measurements, right? And then we will combine them result instead of just estimating only on the one predicate. Basically, we could have like the sum, right? Instead of like just like ket bra O, we can sum of like ket bra OI and then like do the sum. Like how would that change your results if you have like several projective measurements? I think if I'm not wrong, you are considering only one projective measurement, one type of projective measurements like ket bra O, right? But now it's like, for example, like instead of considering just measure like get the probabilities of all zeros, like how about like all the like projective measurement with like only one ones on like one like systems. Like for example, 2 qubits, then you'll be like 0, 1 and 1, 0, and then I sum the result together, and how would that change your result?
Maybe this is maybe you change the computational basis, maybe not change the result, but we just give a specific task to verify our search result. And in if I'm not wrong, maybe you mean this in the numerical.
Or just like, can you go back to the assumptions like at the beginning of your slides, your assumptions about the observable that you kind of assume? Yeah, at the beginning.
Okay.
Yeah.
Yeah, it's this slide.
Yes. So you like you say okay, we observe projected measurements like 0, 0, right? Like right? So could you consider like multiple projected measurements and do the learning task instead of just like estimate the expectation value with respect to this one projected measurements? You just sum of it, and how will that change your results? Like your O will be like sum of I or I ket bra.
Okay, this OBI. So I think this is just dependent on the possible outcomes, the number of possible outcomes, but not dependent on the specific forms of this projective measurements. So if we change this measurements by other project measurements or some POM measurements with constant outcomes, this result still hold. But if you change this measurement at the continuous POM, so maybe the transition or the entangled dates maybe not occur. So I think the results of our results is just dependent on the possible the number of possible outcomes of the measurements.
Right. Could you okay, yeah, so now just like because we are kind of discussing this, right? Could you kind of like construct the observable such that you can tune like how many outcomes that you observed and then trying to kind of generalize the result and show that okay, maybe if you have more outcomes, then this transition rule of entangled data basically doesn't occur, right? You have one extremes where you only have one measurements that you have limited like outcomes, then is what you observe over here. And then now you go to the other extremes where you go to POM, and then this shouldn't be occurs, right? So there's some kind of like transitions in terms of the number of observables that you kind of like place. I don't know, as in just some random kind of thoughts on the possible extension of this work.
Maybe Yeah, you're right. Yeah, this depends on the number of measurements. So one interesting open question that if we use the entangled measurements with
Yeah. So this another thing that I'm thinking of is to use multiple copies. Like if you have access to quantum like memories, and then could you kind of design like could this still be focused over there? Because nowadays like people start to consider like quantum memories, right? What if you have like two copy of data of the quantum state and then you do coherent processing? What will happen, right?
I think any so the methods that can enhance the information interest, the ability of information extraction of the measurements can help to change or helps to enhance the power of entangled data because yeah, this is just because we consider the measurement is so weak, it just have constant outcomes. So
Right.
yeah, I think.
Okay. Yes, fine. I think we can like definitely chat more when we meet in person. Because like the time is kind of like overrun by quite a lot. Then maybe you can like end the seminars now. As in like if the participants have any question, I think they could drop you an email to ask about questions. Yeah. So
Yeah. Have my email. Maybe if you have any further question, you can send mail to me, and I will give answer.
Yeah. Thanks again, Xinbiao, for the very interesting talk, and like hope to see you in person on Thursday. Yeah, maybe.
Yeah. Looking forward to see you in person. So okay.
Yeah. Thanks everyone. Like see you.
Okay. See you. Thanks.